The swinging Atwood's machine is a mechanism that resembles a simple Atwood's machine, except that one of the masses is allowed to swing in a two-dimensional plane, producing a dynamical system that is chaotic for some system parameters and initial conditions. Specifically, it comprises two masses connected by an inextensible, massless string suspended on two frictionless pulleys of zero radius such that the pendulum can swing freely around its pulley without colliding with the counterweight. The conventional Atwood's machine allows only runaway solutions, except for, however, the swinging Atwood's machine has a large parameter space of conditions that lead to a variety of motions that can be classified as terminating or non-terminating, periodic, quasi-periodic or chaotic, bounded or unbounded, singular or non-singular due to the pendulum's reactive centrifugal force counteracting the counterweight's weight. Research on the SAM started as part of a 1982 senior thesis entitled Smiles and Teardrops by Nicholas Tuffilero at Reed College, directed by David J. Griffiths. Equations of motion. The swinging Atwood's machine is a system with 2 degrees of freedom. We may derive its equations of motion using either Hamiltonian mechanics or Lagrangian mechanics. Let the swinging mass be and the non-swinging mass be. The kinetic energy of the system is where is the distance of the swinging mass to its pivot, and is the angle of the swinging mass relative to pointing straight downwards. The potential energy is solely due to the acceleration due to gravity. We may then write down the Lagrangian and the Hamiltonian of the system. We can then express the Hamiltonian in terms of the canonical momenta. Lagrange analysis can be applied to obtain 2 second-order coupled ordinary differential equations in first the equation and the equation. We simplify the equations by defining the mass ratio. The above then becomes Hamiltonian analysis may also be applied to determine 4 first-order odes in terms of and their corresponding canonical momenta, and notice that in both of these derivations, if one sets an angular velocity to 0, the resulting special case is the regular non-swinging Atwood machine. The swinging Atwood's machine has a 4-dimensional phase space defined by and their corresponding canonical momenta, and however, due to energy conservation, the phased space is constrained to 3 dimensions. System with massive pulleys. If the pulleys in the system are taken to have moment of inertia and radius, the Hamiltonian of the SAM is then where mount is the effective total mass of the system. This reduces to the version above when and becomes 0. The equations of motion are now where integrability. Hamiltonian systems can be classified as integrable and non-integrable. SAM is integrable when the mass ratio. The system also looks pretty regular for, but the case is the only integrable mass ratio found so far. For many other values of the mass ratio, SAM displays chaotic motion. Numerical studies indicate that when the orbit is singular, the pendulum executes a single symmetrical loop and returns to the origin, regardless of the value of. When is small, the trajectory describes a teardrop. When it is large, it describes a heart. These trajectories can be exactly solved algebraically, which is unusual for a system with a nonlinear Hamiltonian trajectories. The swinging mass of the swinging Atwood's machine undergoes interesting trajectories or orbits when subject to different initial conditions, and for different mass ratios. These include periodic orbits and collision orbits. Non-singular orbits. For certain conditions, system exhibits complex harmonic motion. The orbit is called non-singular if the swinging mass does not touch the pulley. Periodic orbits when the different harmonic components in the system are in phase. The resulting trajectory is simple and periodic, such as the smile trajectory, which resembles that of an ordinary pendulum, and various loops. In general, a periodic orbit exists when the following is satisfied. The simplest case of periodic orbits is the smile orbit, which Tuffilero termed type A orbits in his 1984 paper. Singular orbits. The motion is singular if at some point, the swinging mass passes through the origin. Since the system is invariant under time reversal and translation, it is equivalent to say that the pendulum starts at the origin and is fired outwards. The region close to the pivot is singular, since it is close to zero and the equations of motion require dividing by. As such, special techniques must be used to rigorously analyze these cases. The following are plots of arbitrarily selected singular orbits. Collision orbits. Collision orbits are a subset of singular orbits formed when the swinging mass is ejected from its pivot with an initial velocity, such that it returns to the pivot. The simplest case of collision orbits are the ones with a mass ratio of 3, which will always return symmetrically to the origin after being ejected from the origin, and were termed type B orbits in Tufilera's initial paper. They were also referred to as teardrop, heart, or rabbit ear orbits because of their appearance. When the swinging mass returns to the origin, the counterweight mass must instantaneously change direction, causing an infinite tension in the connecting string. Thus we may consider the motion to terminate at this time. Boundedness. For any initial position, it can be shown that the swinging mass is bounded by a curve that is a conic section. The pivot is always a focus of this bounding curve. The equation for this curve can be derived by analyzing the energy of the system, and using conservation of energy. Let us suppose that is released from rest at n. The total energy of the system is therefore. However, notice that in the boundary case, the velocity of the swinging mass is 0. Hence we have, to see that it is the equation of a conic section, we isolate for. Note that the numerator is a constant dependent only on the initial position in this case, as we have assumed the initial condition to be at rest. However, the energy constant can also be calculated for non-zero initial velocity, and the equation still holds in all cases. The eccentricity of the conic section is 4. This is an ellipse, and the system is bounded and the swinging mass always stays within the ellipse. 4. It is a parabola and for it is a hyperbola. In either of these cases, it is not bounded. As gets arbitrarily large, the bounding curve approaches a circle. The region enclosed by the curve is known as the Hills region.